Okay, let's do problem 14.16. It's about simple harmonic motion. So let's make a simple diagram first. So that's the horizontal surface, and there is a spring right there, and a block is attached, and it is undergoing SHM, back and forth motion. Initially the amplitude is 0.09 meters. So the amplitude to go from here to here, it's 0.09 meters, and it will also go the same distance back, negative 0.09 meters. To go from here to here, it takes 2.7 seconds. So period would be to go from here to there and back. So one complete cycle is the period, but this is only half of it because it goes from here to there. So you can say that T is 2 times 2.70 seconds, and that is 2 times 2.7, so 5.4 seconds. That's the period of oscillation. Now with this, you can actually calculate the angular frequency, omega, because omega is related to T, and its omega is 2 pi over T, and that is 2 pi over 5.4 seconds, and that gives you, use a calculator, it gives you 1.164 radian per second. Now it says if the amplitude is doubled to 0.18, how long does it take the block to travel from positive 0.18 to negative 0.18? So we need to increase the amplitude. So the new amplitude would be to go from here to there, so twice the distance, 0.18 meters, and from here it goes back the same distance, so minus 0.18 meters. So that's the new amplitude. Now part A asks how long does it take the block to travel from this to this. So we know that omega squared is equal to k over m. That's for simple harmonic motion, mass and spring system. This actually comes from, you don't have to derive it, but it comes from, F equal to kx, negative kx, restoring force, which is mass times acceleration, and that's equal to negative kx, and A would be equal to negative k over m x. If you compare this with the equation for simple harmonic motion, which is A equal to minus omega squared x, then you can compare this k over m and omega squared. They are the same, so that's why omega squared equal to k over m. This omega is equal to square root of k over m. This omega is related to T, so you can write that T, so this means that 2 pi over T is square root of k over m. That means T is equal to 2 pi square root of m over k. So you can calculate the period from this equation. But now if you look at this equation, period of oscillation depends on the mass of the block and the spring constant. It does not depend on the amplitude. So the amplitude, whether it is 0.09 or 0.18, the period of oscillation is still the same. So in A, you can write that T does not depend on the amplitude. So the time to go from here to there would still be the same, which is 2.70 seconds. Now part B, it says how much time does it take to go from 0.09 to negative 0.09. Given this amplitude, what is the time that it takes to go from here to here? So that's the time that we need to find out. So now that this is the amplitude, we should be able to calculate exactly how much time it takes to go from here to here, to this location, from the maximum amplitude, and another time to go from here to there. So let's call this T1 and let's call this T2. So the time to go from here to here would be the difference in these two times. So let's try to calculate this T1. Now to calculate that, you start with this equation, x equal to a cosine omega t, and this equation allows you to calculate the time if you know the angular frequency, amplitude, and the location. So this is the position, which is 0.09 for T1 and negative 0.09 for T2. So you can calculate, let's say you want to calculate T1, 0.09 meters equal to A, which is 0.18 meters, cosine omega T1. So you can write omega T1 equal to cosine inverse. So this goes to the other side, becomes 1/2. 0.09 divided by 0.18 gives you 0.5. That's cosine inverse 0.5. Use a calculator to get this number. Make sure that you set the calculator to radians, because everything we are doing here is in radians. So don't use degrees, otherwise you'll get incorrect answer. So if you use that, you will get T1 equal to 0.9 seconds. Now that's for this location. Now go to another point, which is negative 0.09, and that's negative, so let's do here, negative 0.9 meters equal to 0.18 meters, cosine omega T2. The only difference is that this is positive, here this is negative, that's all. So omega T2 is cosine inverse negative 0.5, because this is negative. So T2, use a calculator, use this in radians, and T2 will come out to be 1.8 seconds. Now to go from here to there, it takes 1.8 seconds. To go from here to there, that's T1, that's 0.9 seconds. So the difference, which is to go from here to here, is the answer. So T will be equal to 1.8 seconds minus 0.9 seconds, and that's 0.9 seconds. Compared to going from here to here, from here to here is half. You would think that the time would be 1/2. 1/2 would be 1.35, but it takes only 0.9 seconds to go from here to here. The reason is that the object has the maximum velocity here and will slow down as it goes towards this direction, and same thing in this direction. And it will be the slowest here, so the velocity would be 0 there, and when it comes back it will start to speed up, and then maximum velocity will start to slow down, and then the velocity will be 0, and so on. So right around this area, this object is moving really fast compared to here and here. So that's why around this area it only takes 0.9 seconds. That's all.